welcome to the deep dive. Today we're plunging into the real brain power inside our computers, CPUs and GPUs. And the big question we're tackling is, how do these two actually work together? And, what does it really take to build something genuinely groundbreaking like NVIDIA's latest Blackwell GPU?
Right. Our mission today, if you will, is to unpack those fundamental architectural differences. We'll take a look inside Blackwell's design, which is pretty amazing, and then explore why competing at this kind of level is, well, it's like mastering multiple different rocket sciences.
We ended up with things like AI accelerators.
Yeah.
We need to grasp that basic split, CPU versus GPU. What's the core philosophical difference?
Yeah, at its heart, it's really a tale of two completely different approaches. You've got low latency versus high throughput. Think of the CPU maybe like a brilliant head chef. Super smart, can handle any complex task you throw at them, designing a new recipe, running the entire kitchen, and doing it fast.
So speed for one complicated thing.
Exactly. Its focus is low latency, completing that single, often intricate task as quickly as possible. That's why CPUs have, fewer but much more powerful cores. They use sophisticated techniques like out-of-order execution, letting them juggle instructions smartly for speed, and branch prediction, trying to guess what's next to avoid delays, plus deep cache hierarchies for really fast data access.
Okay, so the CPU is the specialist printer for complex serial jobs. How does the GPU then sort of flip that script?
It's fascinating, really. The GPU is almost the polar opposite. Instead of that one master chef, picture like an army of junior assistants. Maybe each one has 10 hands, right? And they're exceptionally good at one simple repetitive thing, like flipping hundreds of burgers all at the same time.
Okay, got it. Volume over complexity.
Precisely. That's high throughput. It's optimized for doing thousands, even millions of simple tasks in parallel. So GPUs have hundreds or thousands of smaller, simpler cores. They're designed to kind of tolerate memory latency delays in getting data by just constantly switching between different tasks that are ready to go. The goal is just keeping those computation units busy, always busy.
And for you, listening, this difference is absolutely key to why they do different jobs. CPUs are great for your operating system, game logic, things that happen one after another, serially. But GPUs, their massive parallel power is what drives modern graphics, complex scientific simulations, and critically, the enormous math calculations behind AI and machine learning. The rise of the general-purpose GPU and platforms like NVIDIA's CUDA, that was a real turning point. It took GPUs beyond just pictures.
Okay, so with that architectural groundwork laid, the sheer scale of NVIDIA's Blackwell GPU, it seems even more incredible. What makes Blackwell such a leap in engineering, especially when you think about physical limits? Blackwell is definitely more than just more powerful. Its design is really a clever strategy to push past the physical boundaries of making silicon chips. It packs, 208 billion transistors? An astonishing number.
Yeah.
But here's the kicker, like you said, it's not actually one single piece of silicon.
Because of that reticle limit thing, the maximum size.
Exactly. There's a physical limit to how large you can make a single chip during manufacturing, roughly 850 square millimeters. So Blackwell uses this ingenious dual die design. They essentially fuse two massive dies, two big chips, into a one unified GPU. And they do this using their own special interconnect tech, nVHBI. It provides a crazy amount of bandwidth between them, 10 terabytes per second.
10 terabytes. Just between the two halves.
Just between the two halves. And that, combined with really advanced packaging, it's called CoWES, basically stacking chips very precisely, it makes these two distinct pieces of silicon truly act as one single GPU from the software's point of view.
So they found a way to stitch two chips together so seamlessly it just looks like one bigger, better chip to the developer. And I assume it's also loaded with specialized AI hardware.
Completely seamless for the developer, yes, and absolutely packed. It's got a second-generation transformer engine that includes support for new, very low-precision math formats like FP4 that basically doubles the performance and the size of AI models you can run, especially for generative AI. Then there's the 5th-gen NVLink. That's the tech for connecting potentially hundreds, up to 576 of these GPUs together into one massive supercomputer. You need that for the truly enormous AI tasks. Oh, and even a dedicated decompression engine to speed up data analytics workloads.
Okay, it's a beast. Which brings us to the really big question. If NVIDIA built this marvel, why can't other huge tech companies just, copy it? Or build their own version? What's stopping them?
That's where it gets really complex. It's not just one single rocket science challenge. It's like several interlocking ones. First, just making the things, fabrication. Building one modern chip factory, a fab, costs tens of billions of dollars, and the absolutely critical machines, the EUV lithography machines needed for the tiniest transistors, they cost over $150 million each. And they're essentially monopolized by one company, ASML. They only make maybe 50 or 60 a year for the entire world.
Wow, okay, so scarcity and cost just for the machines.
Right. And then there's the actual process. Achieving good yields, meaning getting enough working chips from each silicon wafer at these incredibly small scales, like 3 nanometers or less, it's incredibly difficult. Tiny imperfections, even a speck of dust, can ruin chips worth millions. It's often described as black magic.
Okay, so manufacturing is hurdle number one, a massive one. What else? The software.
That's the next giant piece of the puzzle. nVidia didn't just build hardware, they built CUDA. They have almost a 20-year head start with this software platform. It's a complete ecosystem. There are over 4 million developers using it now. Thousands of libraries optimized for NVIDIA GPUs. That creates this incredibly powerful network effect. It's very, very hard to displace.
A huge moat built over decades. And then I guess it comes down to the dollars and cents.
You got it. The economics are just staggering. The R&D cost for Blackwell alone was reportedly around $10 billion, just for one generation. NVIDIA's dominant market share and, frankly, their high profit margins allow them to reinvest massively. It creates this virtuous cycle. Huge profits fund huge R&D, which leads to better chips, which secures them priority access to that scarce manufacturing capacity we talked about.
Right. They can essentially outspend and out-innovate because they already lead.
Exactly. So any competitor isn't just trying to catch up to Blackwell. They're facing this multi-generational, multi-billion-dollar arms race against an incumbent that basically owns the whole playground hardware, software, manufacturing access, the developer community. It's the entire system.
So wrapping this up for you, the listener, what this really highlights is that the gap between a general CPU and an AI powerhouse like Blackwell, it isn't just about speed anymore. It's this deep reflection of different design philosophies, yes, but also incredible manufacturing prowess and really strategic long-term ecosystem building, so the whole package.
Yeah, it's not just about designing a slightly better chip. It's about executing flawlessly on building a better integrated system. The true difficulty, the rocket science part, isn't solving just one of these incredibly hard problems. It's mastering and integrating all of them, the physics, the manufacturing, the software, the economics simultaneously, and doing it year after year after year.
For any potential challenger out there, it really looks like a journey as complex, as costly, and maybe as perilous as planning a mission to Mars. Makes you wonder, doesn't it? What parts of this incredible technological race, the architecture, the manufacturing, the software ecosystems, what do you think will most define computing in the next decade? We hope this deep dive gave you some really valuable insights into the world of silicon. Until next time.